Hello, welcome back. This is part 2 of sorting algorithms. This is intermediate sorting algorithms. So we have 3 more to look at, and basically we're learning these separate because they are much faster, but they're also a little bit more challenging. They're less intuitive to write on your own. They're meatier, juicier algorithms that take more time to understand. But they're also, the payoff is that they're faster. And I'm going to prove it to you. I'm going to show you at least one example of just how much faster they can be in this video. But first, I want to add an important note, which is don't be scared. When I've taught this before, I think a lot of students feel bad because they struggled through the beginning elementary sorting algorithms. They weren't able to write everything on their own. That's totally normal. And when you get to these 3, these algorithms are harder. They're stepping it up. Don't feel pressure to write the code yourself, period, but especially not the first time through. So I'm going to give you pseudocode for the adventurous souls who do want to try and implement it on their own. But really, this section is more about walking through the code and understanding how it works, being able to explain the algorithms, not being able to rewrite it word for word, character for character on your first try. So keep that in mind. We're going to go through it. Focus on how it works, focus on being able to explain back to me, for example, what each line of my code does, rather than you feeling the pressure to come up with everything from scratch. Because these are challenging, and these are algorithms created by academics that have been around for a while, that have been tried and tested. So please don't worry, don't be too intimidated. I'm turning nobody away, all right? If the last section was hard for you, that's okay. Don't feel bad that this one's called intermediate. Okay, so our objectives. First, understand the limitations of what we've learned so far. Bubble, selection, and insertion. What's wrong with, well, we shouldn't say what's wrong. What are their shortcomings? We're going to implement 3 sorts, implement merge sort, quick sort, and radix sort. But first, I promised I would show you a demonstration of how much faster the algorithms we're going to learn now are. So the sorting algorithms we've learned so far don't scale well. They actually work pretty well on small, like a 20 item array. They work pretty fast. But they do not scale well if we're working with 100,000 elements, for example. So if we actually tried bubble sort, I'm going to scale it down and just do 10,000 elements. It takes quite a while. I'm going to show you right now. So what I have here, so here's my bubble sort implementation. And down here, I have a little bit of code that makes an array of, oh no, this is 100,000. I can't count. Never mind. It is 100,000 elements. And I'm going to start by showing you bubble sort. Now what this code does, if I just copy this over and change this number to be 10, it just picks 10 random numbers and sticks them in an array. So if I do 100,000, we're going to have an array that's 100,000 random numbers. There shouldn't really be any order, period. I mean, it's technically possible they could be already sorted, but that would be insanely unlikely with 100,000 items. Okay, so I'm going to do this now. I'm going to hit enter. It's going to make the array. That just takes like a split second, but then bubble sorting, it's going to take a little bit. So command enter, I start it. And what am I going to talk about to pass the time here? Well, let's see. What am I even going to say here? I got some time to pass. Well, it's a nice day outside and I'm in here recording. There we go. Looks like it just finished. So I don't know exactly how long that was. I think I also put a cut in the middle of this because I took a sip of water and then I realized that was going to sound really bad on the camera if I'm gulping. So anyway, that was about 20 seconds of my time. Now, if I do the same thing with merge, which I already have in this file, merge sort, we haven't learned it yet, but just watch. I'm going to clear and run the same code. So 100,000 items, but now pass it into merge sort. Wow, look at that. I mean, that's crazy how much faster that was. That was less than a second compared to 20 something seconds. Now, if I added another 0 here, which I'm not going to, remember that bubble sort is quadratic. So that has serious implications. When we add another 0, when we're squaring the time, basically, that's huge. That's a huge difference. So I'm not going to do that. But with merge sort, I mean, we'd still notice a difference, but it's nowhere near the time difference. And we'll talk about what the actual big O is of something like merge sort. But I just wanted to show you there how much faster it is. Maybe that gives you some motivation for learning it. So this faster family of algorithms that we're going to learn, they can improve time complexity from around ON to ON log n. So if you can think back, I'll show you a chart again, but O of n log n is not bad. It's pretty good. It's much better than quadratic time, O of n squared. It's not as good as log n, and it's not as good as O of n, but it's still pretty dang good. So in this section, we're going to learn 3 algorithms that improve time complexity, and we'll also learn why it's n log n, for example. Where does the n log n come from? We haven't really talked about it. We introduced the idea of a log. We said that O of log n is good. It's pretty fast, but we haven't really seen where it comes from. So we'll see that. There's a trade-off, though, as I mentioned, between efficiency and simplicity, unfortunately. So these more efficient algorithms are definitely harder. They're longer, or even if they're not longer in the amount of code, they're just weirder. They're not how we think as humans most of the time. It's not how you would sort something. So they take a little longer to understand. But it's worth it, right? That's a very big difference that I just showed you. And that was only 100,000 items. Now imagine 1 million or 10 million pieces of data. Massive differences in time. So let's dive in. In the next video, merge sort. Hey, welcome back. So the first of the fancier sorting algorithms that we're going to take a look at is called merge sort. It's a very well-known one. It was created back in 1948. A computer scientist / mathematician and all-around smart guy named Jonathan Van Neumann wrote the first ever recorded program of merge sort. It was 23 pages of code for this computer here called EDVAC. It's a very large computer. It was like 6,000 or so vacuum tubes. Writing code back then, obviously very different than it was today, but the algorithm, the idea, was first conceived in 1948. So the idea behind it, it's really a combination of 2 things, merging and sorting. And actually, you could say it's really a combination of 3 things, splitting up, sorting, and merging. All 3 things take place. So it exploits the fact that arrays of 0 or 1 element are already sorted. So if you were asked to sort an array that just consists of the number 1 and that's it, you know it's sorted. Or it's just the number 9, it's sorted. Or it's empty, it's sorted. So merge sort takes advantage of that fact. It works by decomposing an array into smaller arrays. So that's something known as a divide and conquer algorithm, a divide and conquer approach. We split up the larger array we're trying to sort into smaller sub-arrays. All the way down, we keep doing it until we get to 0 or 1 element arrays. So we would take an 8 element array and split it, and then split it, and then split it until we end up with 8 single element arrays, and then we merge them back together. So here's a little visualization. Imagine we have this array here, 8, 3, 5, 4, 7, 6, 1, 2. That is 8 elements. What do? We start, or the code starts, by splitting it in half. So we're dividing it. And we're still not at 1 or 0 element arrays, right? These are 4 elements, so we split again. And now we have 4 2 element arrays. We're still not there, so we split again. Now what we have are 8 single element arrays. So now we merge them together. So let's focus here. We take these 2 arrays and we merge them back. And as we merge them, they are already sorted. We know that they're sorted. So merging 2 sorted arrays is easy relative to merging 2 unsorted arrays. So what we do, we basically just compare the number. Which one is smaller? Well, the smaller one goes first. Which one of these is smaller? Smaller one goes first. Which one of these is smaller? Put that first. 1 goes before 2. Then we repeat the process. Now we're merging this array with this array. But notice this is already sorted. This is already sorted. So now we just make a couple comparisons. Take the first item, compare it to the first item. Which one is smaller? Put that one first. Then we take this item, compare it to that item. Which one's smaller? Okay, put 4. And then we do it again, put 5, and then 8. And then the same thing over here. So we end up with 1, 2, 6, 7, and 3, 4, 5, 8. 2 sorted arrays that are smaller. Now our final merge, we put them all together. And we end up with this 1, 2, 3, 4, 5, 6, 7, 8. So hopefully you can see, yes, this algorithm is a little more complicated, but it involves first splitting up until we end up with sorted arrays, which are 0 or 1 element. That's the base case. That's the smallest thing we get to. We know they're sorted if they're only 1 item long or they're empty. Then what do? We merge them. Merging sorted arrays is easy. Well, compared to merging unsorted arrays, still not that easy. And we sort them back until we finish and we get a totally sorted array. Here's another visualization. Here we have 8 elements in an array, And the very first thing that happens is we split them all up into 8 individual arrays. So now they all have, each color represents the fact that they're an individual array. And then you'll see as we merge them together, they change color. So it starts with the first 2. These are 2 arrays. How do we sort them into 1? 3 and 44. It takes them out and puts them back in that order. They're sorted. So now we have, this is 1 array here. So we have 7 arrays, right? Oh wait, 1, 2, 3, 4, 5. Yes, 7, I can't count. So next, we take these 2 individual arrays and we sort them into 1 and put them back. Now, we take these 2 arrays, the orange and the red, of those 2 items each, and we sort them into 1 array, like this, and then we put that back. Then we have to start on the right side. So this was the left division. Now we take 47 and 15, we sort them from 2 arrays of 1 item into 1 array of 2 items. Same thing with 36 and 26. Now what do? We merge these 2 arrays together, the yellow and the green. There we go. Put that back in, and now we merge our 2 arrays of 4 items at the very end. There we go. So that's merge sort. And as you can imagine, there's a little bit of logic involved. In the next video, we're going to implement the first step, which is merging. So we have to understand how to merge 2 sorted arrays, and then the rest is actually pretty easy. So in the next video, we're going to cover that. We're going to build a merging function. Hey again, welcome back. So this is the first part of writing merge sort, which is writing a function to merge 2 sorted arrays. So again, we assume the arrays are sorted, and all you have to do is return the combination of those 2 sorted arrays. So for example, I already have it written here. Well, I'm not showing you the code, but I have the function call here. 2 sorted arrays, 1, 10, 50, that's sorted. 2, 14, 99, 100, that's sorted. When I run this, I merge them together. We get 1, 2, 10, 14, 50, 99, 100. So 1 array that is returned. So that's basically your job. If you want to try and do this on your own, I'll have a solution in the next video. This part's, well, personally, I always hate saying if something's hard or easy, but I think the logic for this one makes sense. So we'll walk through it though. I have pseudocode. So I jumped the gun on my slides. Yes, it's useful to first implement a function responsible for merging 2 sorted arrays. Given 2 sorted arrays, the helper function should create a new one, which is also sorted. And yeah, it's important. It needs to consist of all the elements in the 2 input arrays. So what do we do if they're not the same size? We'll cover that. And as far as how it should work, this is something we haven't seen, but it should run in O of n plus m time and O of n plus m space. So n and m, we have 2 inputs now to our function, 1 array and then the second array. So n is the size of the first one, m is the size of the second one. Of course, those are 2 that sound very similar, and you probably can't tell when I'm saying n and m, but that's the standard way of saying it, of writing it down. So that just means that if n grows super large but m doesn't grow very large, it should just be O of n plus m. Often, and usually in merge sort, they are the exact same size or 1 element different in real life. But if we're working with something and for some reason we're merging an array of 1,000 items with an array of 1,000,000 items, it should be O of n plus m. So as that 1 grows, anyway, all I'm saying is that you should visit each item in the array 1 time, right? If it was just O of n, that means that it's linear time. You visit each item once, you iterate over it. But if it's O of n plus m, that means that we're iterating over each item in each array once. So here's the pseudocode. Create an empty array. So define a function, takes 2 inputs. Create an empty array that you'll return at the end. And then you start with the smallest values in each input array. You start at the beginning. So have 2 counters, one called I, one called j. I recommend using while loops for this. Personally, that's what I like to do. And you need to have one that starts out, they both need to start at 0. J and I are 2 numbers, start at 0. While there are still values we haven't looked at, meaning while I and j both haven't hit the end of their respective arrays, we're going to take the value of the first array, of the first item, and then compare that to the value of the first item in the second array. Now, if the first item is smaller, we put that in our result array, and then we move on to the next item in the first array. If it's the other way around, if the first array is larger, the item in the first array, then the value in our second array, we take the value from the second array and put that in the results and move on to the next value in the second array. And then once we finish one array, we just push all the remaining values from the other array in. So for example, if we took these 2, we just write them down here, these are our two arrays, and then this is my result that I'm going to return. We start with two counters, I and j, and they start at 0 and 0. So we compare 1 and 2. Which one is smaller? 1 is. So we put 1 here. And then we move on. In this first array, we're now looking at 10. So if I were to put a little marker here, like that, it's not a very great way of writing that, and our marker over here, this is going to bite me, this is going to be annoying to keep track of, is 2. So next time through, we're comparing 10 and 2. Which one is smaller? 2. So we put 2 in here, which means that now we need to shift this over, and now we're looking at 10 and 14. So now which one is smaller? 10 is. So we put 10 in, and then we move this up, not this one. Now we're looking at 14 and 50. Which one is smaller? 14. All right, so then we move this to 99. What am I doing? Get out of there. Okay, 50 and 99, which wins? 50 wins. So then we've now exhausted that array. And what that tells us, if we've hit the end of this, all we do is take all remaining values in this other one, because if this is sorted, and they have to be sorted in the same way, I should have mentioned that. We can't have one in ascending and one in descending. They're sorted in the same way. Whatever is at the end of this array, if we have stuff that's left in the other array, we know for sure it's all greater than whatever, that 50 in this case. So now we just add in 99 and then 100. And now we have successfully merged the two arrays. So that's the approach that I'd like for you to try and take. Otherwise, if you don't want to do it, in the next video, I'll just show you a solution. So this is a first important step for merge sort. All right, welcome back. Now let's write the code to make this work, to merge two sorted arrays. So if you jumped to this video because you saw implementation in the title, I recommend you just go back and take a look at the rough pseudocode, how it's supposed to work, just so you understand what we're doing here. So here I'll start by defining, I have a snippet as always. I'll call it merge, my function, and it takes in two arrays. Let's just do ARR1 and ARR2. And then in here, the very first thing we should make is just make a variable called results. Empty array, and then at the very end, we return results, like that. And then we need to do all of our logic. So the first thing we'll do is make our two little pointers. We're going to start with a variable at 0 and another one at 0, one for each array, and then they'll move through individually. So we'll do let I equal 0, let j equal 0, or whatever. You could call it ARR1 index or something, but I'm just going to go with I. Okay, so now the bulk of our logic, we need to have a while loop that runs while I is less than the length of the array and j is less than the length. Basically meaning while there is still data for us to look at in both. If we hit the end of one of them, remember in the last video what I showed, when we started here, then we hit the end of 50 and there was still data here, we're going to do something else. So this first loop only applies when we're looping through both at the same time. So while I is less than array1.length and j is less than array2.length. Perfect. Now we just do a simple comparison of array2 of j and array1 of I. So it's up to us which one we want to do first. I'm going to say if array2 of j is greater than array1 of I. It's so confusing to try and talk about. If this is our results, we're basically checking if this one is greater than this one, what do? We take this and we put it in results. So if that's the case, we're going to say results.push array. Oh, and I said that backwards. I'm sorry. If this one is greater than this, then we take the smaller one and we put it in there. I don't know why. We're not trying to do descending order. We want the smallest items first. All right. So we're going to push array1 of I if it is smaller, if array1 is the smallest thing. And if that's the case, if we actually push array1 in, we then need to move I. It's no longer going to be 0. We need to move I up by 1. And that's super easy. I++. Okay, so now we have an else, which is a lot of times, well, I guess we haven't covered the edge case if they're the same value. So instead of doing an else if array2 is less than array1, because if we just did greater than and less than, we'd be missing the case of equality. but we can just pick one. We could do greater than or equal to with an else, or do greater than and then have an else, which will catch the case when they're equal and when array 1 is greater. Okay, so if that's the case, otherwise we do results.push array 2 of j, and then we increment j by 1 because now we're moving up. So that would be do we have that scenario? Let's see, in the first time through, we put 1 in here, and then we're looking at 10 and 2. Yes, so now 2 is smaller. So in that case, we add 2 in, which is from array of j, but then we increment j by 1, and we go here. Array of 2, I mean. All right, so if we look at what happens at the end of this loop, let's print this out. Well, we're going to return results, so we don't actually need to print it. It's not complete, but it's getting there. So we end up with 1, 2, 10, 14, and 50. Because what happened is we did this, then this. We did 10, 14, did 50, and then we hit the end because we did 50, and then we added 1 to I, and we hit the end of the array. So this loop broke out. We finished. So what needs to happen afterwards once we exhaust one of them, because remember our condition, while I is less than array 1.length and j is less than array 2.length, once we hit the end, we then just take everything that's left in j and add it in. Or if this was shorter, like here, if we hit the end, we then take whatever's left in the first array and add it in. So that's easy as well. I'm just going to do 2 while loops, and I'll just have a while loop while I is less than array 1.length. What are we going to do? Results.push array 1 of I, and then just add 1 to I. So basically the same logic in here. It's just that we're not doing a conditional check anymore. And I'm going to just duplicate this, but then replace I with j, and array 1 with array 2. Does that make sense? So whatever happens at the end, we merge them as far as we can until we hit the end of one of the arrays. So let's say we hit the end of array 1. That means that array 2 still has stuff in it. So j hasn't hit the end. So j will be less than array 2.length. In our case, if we hit the end, 0, 1, 2, 3, we get 1, 2, 10, 14, 50. That means that j is currently at index of, 0, 1, 2. So we have to add this in, and we have to add this in. And then j will have hit the end. J will be equal to array.length at that point, and then we finish. And we return results. Let's see if it works. It looks good. If we tried something sneakier, like an empty array, and then the array 1, 3, it still works because this loop never runs, right? All that happens is that we have array of 2, so j is less than array of 2, so we just push in all the results, or all of the items in array of 2 into results, and then return that. If we tried, let's see, doing something like 100, and then over here, I don't know, I don't really even have anything worth showing at this point. That won't work, it needs to be sorted. All I want to show is that it works, and it does. Okay, so this is the first part of merge sort. This is the longest part, actually. If you came up with something better, definitely share it in the comments, post on the discussion board. But this is a pretty simple way of doing it, and I think it's pretty legible, pretty easy to understand and walk through. So we're going to use this code in the next video where we add on and actually implement merge sort. Right now, this only works with 2 sorted arrays. Okay, see you then. Hey, welcome back. So now we get to the sorting part of merge sort. And this is actually, the code itself is pretty short. It's only, my solution is 5-ish lines. The problem is that conceptually, it's a bit hard to understand. And that's because most merge sort implementations use recursion. So if you skip the recursion section, I highly recommend you go take a look at that because this is going to seem a little insane if you've never seen recursion before. And even if you have, it's not immediately intuitive to write code that's recursive. So here's how it works. We have our merge function that works. We just assume it works at this point. If you didn't write it, just go to the last video, copy the code if you want to try and implement this yourself. But again, don't feel bad if you can't. This is really about the concepts, how it works, not about you being able to write it from scratch immediately. Okay, so merge sort. We have our merge function takes 2 sorted arrays. Now remember, the goal is to basically keep breaking up the array into halves. So how do we break an array, just a single array, into a half, 2 halves? Think about that. My recommendation is to use slice. So array.slice, and you go from 0 until the middle of the array, and then you go from the middle array until 0, and that gives you 2 halves. And then what are you going to do with each one of those halves? Well, you're going to call merge sort again, and you're going to break each half into its own halves and keep going recursively. And what's our base case? When the arrays, their length is less than or equal to 1, meaning that it's 1 or 0. Okay, so that breaks them all up into these small elements, these small arrays, using slice recursively until, again, our base case is we hit the end. Array.length is less than or equal to 1. Then once we have those small arrays, we merge them back using our merge function that we've already written until we're back at the full length of the array. Now, it seems simple when you write it this way, but the code, it gets confusing when you're writing it recursively. I'll just put it that way. But that's pretty much it. So once the array has been merged back together, we return the merged array at the very end. Okay, so if you want to take a stab at this, definitely do it. But in the next video, I'll walk through it. Remember, recursion is kind of crazy. It can be a bit of a leap to get there. So don't feel bad if you can't get this one. Okay, see you in the next video. Okay, so let's get writing our own merge sort. So I have a new snippet again. I have our merge function that works from 2 videos ago. We can get rid of this line for now. Now I'll define our merge sort function, which takes a single array. And if we go back to our pseudocode, all that we want to do is keep splitting it up into smaller arrays and calling merge sort on those arrays until the length of the array is 1 or 0. So we can start with the base case if we want. If array.length is less than or equal to 1, we're going to return the array. Not array1, array. So right now, that doesn't mean much. Basically, we're not doing any recursive calls. Remember, every recursive function has a base case and then the recursive case, the recursive function call. So we're going to call merge sort on something again. But it needs to be on the 2 halves of the array. So how do we split this array in half? So for example, if I call merge sort down here on this array, 10, 24, 76, 73, 72, and 1. So how do we split this in half? So if we just took this, I recommended using slice. So if I save this to a variable, var arr equals that. How do we splice it or slice it in half? Well, we go from 0 for the left side. We go from 0 until what? How do we find the midpoint? Well, we could take the array.length divided by 2 and then floor that. All right, so remember binary search, we did the same thing. So that's what I would do. I would do math.floor of array.length divided by 2. And that gives us 3. So then I would do array.slice from 0 to 3. And that gives us the first 3 items. And then we need to do array.slice from 3 to what? We need to do we can actually just do array.slice 3, and it will go from 3 until the end. That's how it works. We don't have to pass in the second number if we don't want to. So that will split the array. That's our first step. And then we'll call merge sort on each of those. So let's just write that code to start. So we can define the midpoint here. So let midpoint, or let's just call it mid, equal math.floor, just the same thing we saw, array.length divided by 2. So that gives us the halfway point. Then we're going to say the left side equals array.slice from 0 until the midpoint. And then we'll say the right side equals what? The right side is going to be array.slice just from midpoint until the end. So now we've split that array into 2 pieces. I'm missing an R here. There we go. Now comes the tricky part. Instead of just doing left equals array.slice, I'm actually going to call merge sort array.slice. And same thing here, merge sort array.slice until the end. Okay, so what's happening here? If we called this the first time through with this array, array.length is not less than or equal to 1, so we skip that. We find the midpoint, then we find left and right. So if we focus on left, we're calling merge sort again on this array that you can see right here. So that goes through, and it's called again. Array.length is not less than or equal to 1, so we skip that line, and then we split it in half again, and now we call merge sort on the left and right. And then one time through, one of them has length of 1. So we return that array, but the other one has length of 2 because there's 3 items. So we call merge sort again. And then at that point, we have 3 single item arrays. And now we have to worry about merging them back. And this is the other bit of magic. We merge the left and the right. So this is the code, and I'm going to walk through line by line how it works. We're going to step through the call stack with a smaller version, but let's just make sure that it's working. So if I execute it, it looks good. 1, 9, 10, 24, 72, 73, 76. Okay, now let's call it on, let's do 4 items. And I'm going to put a breakpoint right here. Now if we look at what happens just with these 4 items, I'm going to step through it. So I'm going to run the code. And let me close the console so we have more space. Look at our call stack over here. Okay, here we go on our journey. So we start and merge sort is called on this array. It's 4 items long. So this first thing does not happen. Then we find the midpoint, which is 2. Now here's the first thing. Watch what happens to our call stack. We are recursively adding, so there's another merge sort that's been added to the call stack. And if you look now at this merge sort, it's been called on that left half, right? So that left half is just 10 and 24. Is the array.length less than or equal to 1? Nope. So we skip it. And what happens again? We find the new midpoint, which is just the middle of this array. We're calling merge sort on what? If we look at our stack again, there we go. We're calling merge sort on a single element, 10. All right, now, this time array.length is less than or equal to 1, right? So we're going to return the array of 10, and you'll see it pop off the stack here in just a second. Return value array, and it popped. Next, we're back to this one. So now we're back to, we left off right here, right? This is a hard thing about recursion. I wish I had a whiteboard diagram this all out, but we were waiting. This function call waited for left to go all the way until it returned something, and now right needs to go all the way until it returns something. So right on that second half is 10, 24. We split it, and the right side goes in, and we get the array of 24. Array.length is less than or equal to 1. So we return array, and you'll see it pops off the call stack in just a second. Now we merge the left and right, 10 and 24. And when we merge them together, it calls merge. All this code happens, and at the end of the day, we end up merging and then finally returning. And watch the call stack. Now we pop off again. Now this time we finished left, right? That was waiting. In this code, we were waiting to merge the left side. Now we need to do the right side. We never even ran this line. So now the right side is now going to go. And if we take a look, it's calling merge sort again with, what is it passing in? Just a moment. There we go, 76 and 73. So array.length was not less than or equal to 1, so we didn't return it, so we move on. Now we call merge sort on the left side, which gives us 76. The array.length is less than or equal to 1, so we're going to return array, and you'll see it pop off that call stack. Keep going. There we go. And now we're back here at merge sort for the right side. It's crazy, I know. This is the hard part to understand, but we're back here, and this time we're calling it with 73, array.length less than or equal to 1. That's true. We return that array, which is 73, pops off the call stack. Now what we have is left and right. So left is 76, right is the array 73. We merge them together, so we call back up here, go through this, merge them, and then eventually we return results, which is the merged array. And now we return that from this merge sort call to our original call of merge sort, which was waiting. So we have left and right that have now been merged. Well, they haven't been merged together, excuse me. They have been sorted, they've been split up and sorted individually and then merged. And now we have two arrays that are 2 items long, and we merge those together with our final merge, left and right. So now this code takes a bit longer because we've got 2 pieces of data for each one. But you can see results down here. We return results to merge sort, So now we have 10, 24, 76, 73, and that is what we return out. And finally, I think if I show the console, we end up with that return value. Whew. So as you can see, it's a lot to keep track of in your own, just 4 elements, trying to keep track of it all in your head can be a lot. So I diagrammed it out, and let's just take a look at the actual order things happen in. So when we call merge sort on 10, 24, 76, 73, first thing that happens, array is this array. We check, is the length less than or equal to 1? No. So we find the middle point, and then we call merge sort on the left side from 0 until the midpoint. So this is called merge sort of 10, 24. So then in that code, if our list is 10, 24, it's still not less than or equal to 1, the length. So then we call merge sort again on the left. And now, this time, the length of this array is less than or equal to 1. And in that event, we return array. So we return 10. So now this merge sort of 10, 24, the list of 2 items long, it now has a value for left. So next, it finds the value for right. It was waiting for this to come back, remember? Now it came back, so it moves on to the next line, right. So now we call merge sort of the right side, which is 24. Merge sort of 24, the length of that array is less than or equal to 1, so it returns 24. So now we have our left and we have our right. So now we can move on to this line, merge left, right. So when we call merge left, right with 10 and 24, remember our merge function takes the 2 sorted arrays, it merges them, and that returns a value, which is the array 10, 24. Yes, it was already sorted, but ignore that part. Our code doesn't know that. So it returns a value now. So that was returned from this merge sort call, which was the left side of our first merge sort. So now our very first merge sort was waiting, and it has a left side returned. Now it's going to do the whole right side. So we call merge sort on 76, 73. In that code, the length is not less than or equal to 1, so it computes the midpoint, and then it does the left side merge sort of 76, which that is a 1 item array, so it returns the value 76. Then this right side, which was waiting, we completed this side. Now we're going to merge sort the rest, and that gives us 73 as a return value because it's a single item array. Then once again, we move on to this line. This was waiting, merge left and right. Well, now we have our left and our right, so we merge them, and that returns 73, 76, 2 item array. Then this merge sort up here now has the left and the right that it was waiting on. So it got this, then eventually this. Now it can actually merge left and right. And to do the left and right merge, we end up with this, 10, 24, 73, and 76. I know it's a lot, but remember, I've said this a couple times, just focus on being able to explain what's happening or walk through. If you have a whiteboard or a piece of paper, I think it can be really helpful to write down exactly what's in the call stack at any given point. And I recommend you don't try it on a super long array. If you go into like 6, 7 items, it takes a lot more time and a lot more space to diagram. Please don't feel too intimidated by this. In the next video, we'll talk about the big O of merge sort. All right, welcome back. I just want to quickly talk about big O, time and space complexity for merge sort. So we haven't mentioned it really, although I showed you in the very first intro to merge sort video how much faster it is, at least anecdotally, compared to something like bubble sort. But the best case, the average case, and the worst case for merge sort are all the same, O of n log n. So unlike something like bubble sort did okay. It was, I wouldn't even say okay. It does pretty poorly. It's quadratic and squared time, unless the data in the best case is already sorted, in which case it improved to linear time, O of n. Merge sort has no such, how do I want to say this? There's no edge case like that in merge sort. It doesn't care what the data looks like. It doesn't have an impact. It's going to split it up over and over and over and merge things over and over and over, no matter what the input is. If it's already sorted or if it's reversed or totally random, it doesn't really matter. So that's the first point. Now, the second thing is, why is it n log n? Where does that come from? And definitely I would not expect you just to know that or even necessarily to be able to compute that right away. But here's a basic overview. So if we start with an array of 8 elements, so this is showing at the end of the process merging them together, but let's say we're starting here and moving upwards. So we have to split it into 2 pieces. So that's one decomposition. Then we split it again, and that's another decomposition, and then again until we get items that are arrays that are 1 item long. So what's the relationship here? If we have 8 items in the array, n is 8, how many times do we have to split in order to get single element arrays? In this case, it's 3. But if instead we had an array of 32 items, I'm not going to type it all out, but imagine that I'm just writing the length here. So we have an array of 32 items. We could do a split, which gives us one array of 16 and another of 16. And then we could split that again, which is what would happen. We'd get an 8, 8, 8, 8. So 4 8-item arrays. And then we split that again. And what do we get? We get 8 4-item arrays. And then we keep going. And I am not going to count these precisely. It doesn't exactly matter anyway if I get the number right. The point is, though, eventually we're going to end up with 32 1-item arrays. Now, how many splits did we have to do to get there? I'm not counting. Please don't hold me accountable here. How many splits? Well, here's the first split, the second, the third, the fourth, the fifth. So as n grew to 32, we had 5 splits. When n was 8, we had 3 splits. What's that relationship? Well, going back to the big O section, that's log n. Now remember, we're talking about base 2, so log base 2 of n. What that really means is 2 of what power gives us n. So in our case, if we have 8 elements, we take 2 and raise it 3 times, 1, 2, 3, to get 8. Or if we have 32 elements, that means 2 times 2 times 2 times 2 times 2. 2 to the 5th power is going to give us 32. So that's where the log n comes from. As n grows, the length of this array, the number of times we have to split it up grows at the rate of log n. Now, what about the n log n? Where does that come into play? Well, each time that we decompose it, we have O of n comparisons when we're doing the merge. So for example, let's take a look at this row right here. This is on the way back to the merge towards it's the last step of merging. There's always 8 items we're comparing each time through, right? We're not adding or removing items at any point. We're just splitting them up and moving them around. But there's always 8 things total. So here, we would start and compare 1 and 3. That's a single comparison. And then one of those is chosen, which is 1. So then we move on and we compare 2 and 3. And then we compare 3 and 6, and then 4 and 6. And at the end of the day, we have O of n comparisons on each of these. So as n grows, the merge algorithm itself, not the merge sort, just the merge, has time complexity of O of n. So if we have 1,000 items in the array, there's roughly 1,000 comparisons that need to be made. If we have 8 items in the array, there's roughly 8 comparisons that need to be made to merge. So in total, we end up with n log n. So O of log n is the number of decompositions. As n grows, there are the number of times we split n, the number of times we split the array grows at the rate of log n. But then each time we do split, each decomposition, we have O of n comparison to actually perform the merging. So in total, we end up with O of n log n. So if we look at a chart, here's O of n log n. You can see it's way better than something like O of n squared quadratic time. It's not as good as O of log n, of course, or linear time O of n, but this is actually the best that we can get for a sorting algorithm, unless the algorithm itself takes advantage of some weird quirk in the data. So there's an algorithm we'll look at called radix sort that uses a particular quirk of numbers, and it won't work to sort anything else. But if we want a data agnostic sorting algorithm, the best we can do is O of n log n. So merge sort is doing great. It's always O of n log n, best, worst, and average time. And then finally, space complexity. So this is a bit different compared to things like bubble sort, which have a constant space complexity. When we talk about merge sort, as we have a larger array, we have to store more arrays in our memory, and not in our memory. We have to use more space. So that is a trade-off. Now, usually we care about time complexity, but if space is a consideration, then absolutely something like merge sort takes up a lot more space compared to bubble sort or any of the other earlier sorts. Okay, so that is the big O of merge sort. Next up, we have a whole other fun sorting algorithm. See you then.